pause on elliptic curves with complex multiplication. Today we will be discussing modular curves and the CM points on modular curves. So let's first recall what we have discussed so far in our previous 3 lectures. So recall, we have in lecture 1, we discussed the definition of elliptic curves with complex multiplication. Lecture 1, we defined elliptic curve with complex multiplication. Namely, elliptic curve is a smooth algebraic curve of genus 1 defined by a Weierstrass equation y squared equals to x cubed plus ax plus b as long as the characteristic of the field is not 2 or 3. And then the endomorphism ring, so endomorphism over k bar of E, when the characteristic of k is 0, is either isomorphic to Z or isomorphic O, which is an order of an imaginary quadratic field K equals Q adjoint square root of D, where D is negative, right? And when the second case happens, we call such elliptic curve having complex multiplication. So lecture 1, we defined our object of study in this course. And then in lecture 2, so lecture 1, we really, what we did is we defined the elliptic curve and started the structure of their endomorphism ring. And we discussed that the only possibilities are either Z or an order of imaginary quadratic field when the characteristic was 1. But we actually didn't prove, in lecture 1, we did not prove the existence of any elliptic curve with complex multiplication, let alone if you were asked, okay, if I give you any order in a imaginary quadratic field, does there exist an elliptic curve where the endomorphism ring is actually isomorphic to that order? So we did not discuss the existence of such elliptic curves. We just discussed the possibility of the existence, right? So then in lecture 2, we actually very explicitly construct CM elliptic curves. Over C. So namely, we discussed that the idea is given any order O in a imaginary quadratic field, we construct the CM elliptic curve whose endomorphism ring is isomorphic to O. Isomorphic. And we did this by constructing lattices. Constructing lattice Z plus Z tau inside the complex plane. Right. So we discussed that given any imaginary quadratic field and any order in that imaginary quadratic field, we could construct a CMT curves, a set of CMT curves whose endomorphism ring exactly is isomorphic to that order. And the construction is essentially take this order and construct a proper fractional ideal of this order. And then when I embed this imaginary quadratic field into my complex plane, choose one of the 2 embeddings, then the image of this proper fractional ideal will naturally become a lattice. And the endomorphism ring of this lattice is exactly O. Okay, great. So that's lecture 2. Is we actually explicitly constructed CMT curves, and moreover, from this construction over C, we could very explicitly see the complex multiplication, right? So in this case, we actually see that for a curve defined over C, it equals to the quotient C mod out that lattice. And the addition law on the elliptic curve is explicitly given by the addition law on the complex number C. And then the complex multiplication is also given by literally the numbers, a complex number multiplying this complex number in C. So this justifies the name multiplication, right? Okay, so lecture 2 gives a very concrete picture of CMP curves defined over C, and also show the existence of CMP curves. Actually, moreover, from lecture 2, we deduced that for any order O, there are finitely many isomorphism classes of the curves whose endomorphism ring is isomorphic to O. And which in lecture 3, we use this fact to show that actually CMP curves are algebraic. So even though we constructed it defined over the complex number C, they always admit a model defined over a number field. And that number field, we can also very explicitly bound this degree. So that is what we did in lecture 3. So what we did in lecture 3 is we looked at all elliptic curves. These are parameterized by the upper half plane modulo the SL to Z action. So the point is, given any number tau in the upper half, so the point is, given any number tau in the upper half plane, we can get a lattice lambda, which is Z plus Z tau. And then this SL to Z action exactly helps you model out the homosity and also a change of basis. Okay, so upper half plane modulo SL to Z action exactly corresponds to the set of all lattices in the upper half in complex plane C up to homosity, which in lecture 2 we discussed that this corresponds to exactly the set of elliptic curves defined over C. And moreover, we discussed the CM points. The CM points on upper half plane modeled SL to Z. Actually, we said without proof, we said that it actually turns out to be a genus zero Riemann surface. So that is called Y1. This is a genus zero Riemann surface. With a puncture. And when we compactify it, we get X1. This is a compactification. And it is given, we compactified it by adding points on the upper half plane. Now we get with the extended upper half plane and model out this SL to Z action. Our action is on the left. And then this, if you look, this quotient is called X1, and this is a modular curve. And the difference between X1 and Y1 is exactly X1 has one extra point compared to Y1. And that extra point is called the cusp of X. Okay, and we discussed the CM points on the modular curve. We discussed this curve, this X1, right? It has a model over Q, so it's actually, you can think it as a P1 over Q, where the function field is given by Q joint J function, which is exactly J invariant of the curve. And we talked about the CM points on this modular curve, namely the CM J invariance. The set of CM J invariance over C, we discussed two properties about it. So first of all, this CM J invariance, these are so-called singular moduli. And first of all, these are algebraic. And the algebraic follows from the fact that in lecture 2, we already discussed the set of all CM curves with the fixed order O. There are finitely many of them up to isomorphism. So they're algebraic, and and also every Galois conjugate, every if I apply an automorphism of C on my elliptic curve, then it will not change its endomorphism ring. And second of all, these J invariants are integral. So the CMJ invariants are algebraic integers. And this tells us, for example, that a CMJ curve have everywhere potentially good reduction. Okay, so this is what we discussed in lecture 3. In lecture 3, first of all, we look at all the elliptic curves together, and we look at the CM ones inside this family. And second of all, we discuss some properties of CM elliptic curves, right? So today, so we can think it as our previous 3 lecture is with definition of the object we want to study. So the lecture 1 is the definition. And the lecture 2 is the construction or show the existence of the objects we are trying to study. And then lecture 3 is in some sense properties, some of the properties. So the J invariants being algebraic and integral. Okay? There are some properties of sampling curves. And today we want to talk about application. So finally, we can discuss why. Why do we care about CM elliptic curves? Why are they important? Okay, so application or why are CM elliptic curves important? So apart from themselves are very interesting objects because they have a bigger endomorphism ring, they have properties that other elliptic curves don't. Themselves are already interesting objects to study. Well, that's fair. But what I want to discuss today is that we can also use CM curves as tools to study other problems. Okay, so the problems I want to discuss today is the Diophantine problem. This is essentially one of the origins of all number theory and arithmetic geometry, right? So the point is we want to study integer solutions to polynomial equations. To polynomial equations. So the most famous Diophantine problem probably is Fermat's law theorem. Which says that if I consider the integers equation x to the n plus y to the n equals to z to the n, where n is greater than 2, the only integer solutions are the ones satisfying x, y, z equal to 0. All the integer solutions are the ones, at least one of the x, y, z's is 0. This is one of the most famous Diophantine problems. And the proof of Fermat's law theorem heavily relies on elliptic curve. And actually the key ingredient we're going to introduce today. Okay, so then in general, the starting Diophantine problem, well, it starts as integer solutions to polynomial equations, which means that this is the same as saying starting rational points on algebraic varieties. Because polynomial equations will define algebraic varieties, and the set of integer solutions will naturally correspond to rational points on these varieties. And to start this problem, well, we can start from, for example, Fermat's law theorem, right? We can start from the case where the algebraic variety of dimension 1, namely rational points on curves. This is this is the problem that's, as I said, very, very classical. It comes from the starting point of all number theory. But on the other hand, this is one of the problems that is currently most actively being studied in the area of arithmetic geometry today. So there are numerous results coming out every year on this topic. Okay, so so let's talk about it. So to begin, let's actually start. Well, since we're talking about elliptic curves in this course, let's start by talking about rational points on the curves. So let E be y squared equals to x cubed plus ax plus b be an elliptic curve defined over Q. Curve with A and B rational numbers. So this is an elliptic curve defined over Q. And let's study the set of xy on EQ, meaning that very concretely just rational numbers xy which satisfy this given Weierstrass equation. Okay. So what do we know about this set? So first of all, using the group law, that we know that EQ is an abelian group. Something special about the elliptic curve compared to any other algebraic curves, right? So the set of rational points actually is not just a set, it has a structure. It forms an abelian group. Okay, so then what do we know about this group? So first of all, the Mordell-Weil theorem Mordell-Weil theorem says that EQ is finitely generated. Okay. EQ is finitely generated. Then suddenly go to the fundamental theorem of finitely generated abelian groups in algebra. So fundamental theorem of finitely generated abelian groups tells us that, well, if I have a finitely generated abelian group, it is isomorphic as a group to Z to the R direct sum, a torsion sum, which usually is denoted as E tor. So this is a finite. Okay, so this is, so if I have a finitely generated abelian group, I will have a free part. So this is the free part. So this integer R is called the rank of EQ. It's a free, well, every abelian group is a Z module, right? Then it's a finitely generated Z module. It will have a free part. And this R is the rank of this free part. So it's often referred to as the rank of EQ. And then there will be a finite part, the torsion part, called the torsion subgroup of EQ. Okay, so great. So now we know a little bit of the structure of what EQ is as an abelian group. So next, what do down to two parts, right? The rank part and the torsion part. What do we know about each of the parts? So recall from previous lectures. I guess this is really lecture 1. So we know that if I look at for any positive integer n, we know that for any positive integer n, kind of greater than 1, for any positive integer n, if I look at the n torsion of E over Q bar, this is isomorphic to Z mod NZ squared, right? Over Q bar, the torsion subgroup is big, it's very, very big, right? It's infinitely generated. But then the question is, how many? So how many of these n points of these points are actually defined over Q. Answer to this question is we also know this question actually. So by the work of Mather, so Mather showed that for any Q, the subgroup, this torsion subgroup, is isomorphic to one of the following the following 15 groups. There are only 15 possibilities for this torsion subgroup. Namely, you can either have a cyclic group Z mod NZ, where N is from 1 to 10, or N equals to 12, or it is not cyclic, it's Z mod 2Z cross Z mod 2NZ, where N is between 1 and 4. And moreover, each of these groups appear. This group shows up for some E over Q. Okay, so the set of rational points for elliptic curve defined over Q has a free part and a torsion part. And then by the work of Mather, we know that this torsion part has only 15 possibilities. And also all 15 possibilities do show up. And it's also very explicitly computable because what you do is you take the elliptic curve over Q, pick a prime, as long as it's not too small, pick a prime where this E is good reduction, and you reduce small this prime. Then you'll see that the torsion subgroup actually will inject into the set of groups it will inject into the point of the reduction. So from this reduction method, we can actually very explicitly compute the set of rational torsion points on any elliptic curve E. Okay, and you can actually practice that with magma. So for elliptic curve defined over Q, the torsion part, we have a relatively good understanding, and we can very explicitly compute it for any given elliptic curve. But on the other hand, the rank part is much more mysterious. Okay, so the rank of EQ is more mysterious. So what do I mean by mysterious? I mean in two ways. So first of all, we don't know whether there are only finitely many possibilities. So point one is we do not know whether the rank of EQ is bounded. There's an absolute bound. So other word is whether there are, just like the torsion, there are only finitely many possibilities. We don't know that. And two, we have a deterministic algorithm to compute it. So let me just say how to compute. With algorithm that guarantees to determine the rank for any if you are given an arbitrary elliptic curve. Okay. In practice, of course, there are methods. If you go to LMFDB and open any elliptic curve there, it doesn't know the rank. We have methods to compute the rank in practice, but we don't have a provably algorithm that will always terminate. Okay, and also some of the rank computations that we currently have actually are conditional. Some of them conditional on GRH or conditional on some other conjectures. That is actually a very interesting topic to discuss. Okay. Anyway, so in general, the rank of a elliptic curve defined over Q is way more mysterious. And one big conjecture in this direction is the Birch and Swinton-Dyer conjecture. So Birch and Swinton-Dyer conjecture. It conjectures that the rank of an elliptic curve over Q is determined by its L function. It conjectures that the rank actually equals to the order of vanishing of the L function of this elliptic curve at its central point. I have not defined the L function for you, so let me just say that L function is determined by, it contains the information of the number of points on reductions of E at all primes P. Okay. So I have not defined the L function for you, and I'm not going to define today at least. And all I want to say is that take your elliptic curve E and consider its reduction at all the finite primes. At the places where you have good reduction, you will get an elliptic curve defined over a finite field. And then you can count the number of FP points on this elliptic curve defined over a finite field. And all of this information, at each P, you get a number. All of this number, together with the band reduction data, put together, gives you this L function. Okay. And one way to think about it is this is, in some sense, like a local global person. Means that this conjecture believes that the number of Q rational points on elliptic curve E is determined by all of the local at all the primes. That's one way to think about it. Okay, so this conjecture in general is wide open. There are actually some cases that are known, and all the known cases are somewhat related to CM curves. So first of all, there are lots of work directly studying the BSD conjecture on 4CM elliptic curve. Okay, there are some results about the BSD conjecture explicitly for elliptic curves with CM. And second of all, another large part of known cases comes from the work of Grosstaghi and Kolivani, and in which their work heavily relies on the usage of CM elliptic curve. Okay, which I'm going to discuss a little bit today. Okay, so the point is one thing I want to discuss today is the work of Grosstaghi. So the point is to use CM elliptic curves to construct rational points on elliptic curves. Okay? So the idea is, so the point is, one thing, if I want to start a set of Q points from E, I need to be able to somewhat canonically constructing rational points on it, right? And how do I do that? Apart from actually constructing points, instead of you give me an E, I do a search, right? I just try numbers and see whether I can find a point. Well, their way, so in their work, there is a method to explicitly construct rational points on the curves using CM theory. So these points are called Hegener points. Okay. Well, to start this, we need to actually, okay, so this is what I want to discuss today, a little bit of application on how using CM curves to study this very classical arithmetic geometry problem, namely studying rational points. Okay, so first of all, to start, let me actually introduce, to do all of this, let me first introduce modular curves. We have already seen examples of modular curves. we already seen the non-packed modular curve Y1, the compact modular curve X1. Okay, so but today we'll talk a little bit more. So we know that Y1 is obtained by the upper half plane mod out the SL2Z action. And X1 is given by the extended upper half plane mod out the SL2Z. I want to construct more. And to do that, I'm just going to give you some subgroups of SL2Z. So namely, consider the group homomorphism SL2Z map to SL2 Z mod NZ, where n is a positive integer. And the map is exactly this reduction map, ABCD map to ABC. This is the mod n action. It turns out that this map phi, so phi is actually surjective, which is not obvious at all. C is actually surjective. And then the kernel of phi, kernel of phi is very clear. These are matrices A, B, C, D inside SL2Z, such that if I mod n, A, B, C, D goes to identity 1, 0, 0, 1, mod n is a subgroup often denoted by gamma of n. And this is called the principal congruent subgroup. Subgroup of level n. Okay, so this is one family of subgroup of SL2n, very naturally obtained. Okay, I gave you a homomorphism and I took its kernel. This is a set of normal subgroups. Definition. Let's define a family of subgroups of SL2n more generally. So congruent subgroups. A subgroup gamma of SL2n, SL2Z is called a congruent subgroup if some gamma of n is inside gamma or some capital N. So as you see that the larger capital N is, the smaller gamma of n is, right? Because well, yeah, you can actually very explicitly, this is the finite index subgroup of SL2Z, and you can actually explicitly compute the index of gamma of n inside SL2Z. And you'll see that this index grows with respect to capital N. So this means that if I give you any subgroup gamma, right? And can I find, when I shrink this capital N, can I find a gamma of n when capital N is large enough? Can I find a gamma of n inside this gamma? If there is a gamma of n inside gamma, then this subgroup gamma is called a congruent, if it contains a principal congruent subgroup. And if that's the case, then gamma called is called a congruence subgroup of level n. Okay, so let's look at some examples of congruent subgroups. The two most important examples are the following. So first of all, well, let's first of all look at gamma 1 of n. So gamma of n are ABCD, where ABCD are literally congruent to 1, 0, 0, 1, right? Okay, gamma 1 of n is give you a little bit of freedom. So gamma 1 of n contains the set of subgroups elements ABCD in SL2Z such that ABCD 1, 0, 1 star mod n. So I give you the freedom of this upper right corner entry. Okay, the upper right corner entry does not need to come with 0 mod n, but it's clear to see that gamma of n is inside gamma 1. It's a subgroup. It's less restricted compared to gamma 1. Okay, and then another family of congruent subgroup is so-called gamma dot of n. This for the same n. So it's ABCD in SL2Z. And all I'm asking for is C to be 0 mod n. Star, star, 0, star, mod n. So all I'm asking for is the element C is congruent to 0 mod n. So then it's less restrictive. So gamma 1 of n clearly is inside gamma 0. These are two families of very important congruent subgroups. Okay, so what's the usage of congruent subgroup? Well, now definition. Now we are ready to define modular curves. The point is congruent subgroups gives you modular curves. So let gamma in SL2Z be a congruent subgroup. Then the modular curve y of gamma is defined as the upper half plane mod out the gamma action. And this is actually a Riemann surface. And also we can define the compactification x of gamma, which is simply the extended upper half plane mod out gamma. So this is one reason why when we compactify Y01, remember we said that, well, Y01 is a two-sphere missing a point. If I want to compactify it, I can naively add back that point and call it, right? And the reason we actually went through we actually, instead of just adding one point to Y01 and call it, we actually added in a whole copy of P1 of Q into our upper half plane, right? And then mod out the gamma action to obtain that one point. One benefit is exactly now we can upper half plane to naturally compactify all the other modular curves. Right? So the point is you see that gamma is inside SL2Z. Actually gives rise to let's take the upper half extended upper half plane mod out gamma naturally covers the extended upper half plane mod out SL2. So this means that x of gamma is a finite cover of x01. Okay. Then the set of points in x of gamma that's not in y of gamma are called cusps. You can also think it as I have one cusp in x01 and I take the pre-image of this cusp inside this covering. Okay. So these curves are exactly called modular curves. And okay, so when gamma is gamma of n, the principal congruent subgroup, gamma 1 of n, or gamma 0 of n, then these curves are usually denoted as correspondingly y of n, y1 of n, y0 of n, x of n, x1 of n, and x0 of n. Okay. Then these modular curves, so these are the modular curves. This is notation, have natural think about x or y, think about y1, for example. So let's think about y1, right? Every complex point, if I take P, that's the complex point in y1, it naturally corresponds to an elliptic curve. Right? It's one-to-one bijection to an elliptic curve, isomorphism class of elliptic curve defined over C. And these modular curves also natural modular notations. And let me do the y0 and the y1 as examples. So let's first do y1. If I take y1 of n, y1 of n corresponds to a pair E, comma Q, where E over C is an elliptic curve, and Q is a complex curve of order exactly capital N. Means that n of Q equals to the origin and any other and D of Q is not trivial for any D divides Q divides N for any D smaller proper divisor. Okay, and also then this is up to equivalence. I have E1 Q1 equivalent to E2 Q2, then equivalence means there exists a phi that is isomorphism from E1 to E2 such that phi of the point Q1 is Q2. Okay, great. So this means that from its modular interpretation, you can very explicitly think about what is the degree of the map from y1 of n down to y1, right? Because on each elliptic curve, how many pairs of EQ are there, right? So degree is just the number of elements on my elliptic curve whose order is exactly capital N, right? So it tells you the degree. Okay, so this is y1. So every point, every complex point on y1 corresponds to a complex elliptic curve together with a point, a little bit extra data, together with a point of order exactly N. Okay, next, let's talk about y0. So for y0 of n, if I take a C point on y0 of n, then it corresponds to also a pair of elliptic curves. So there are two ways to say this. One way to say it is a pair E, comma C, where C is inside EC is a subgroup of cyclic of order n. Cyclic of order, and then is the equivalence is given by E1 C1 is equivalent to E2 C2 if there exists a phi, again, isomorphism on the elliptic curve, E1 to E2, such that phi of C1 equals to C2. Phi of C1 equals to C2. But note that C1 is a subgroup and C2 is a subgroup. For example, you can think about the case where you have where E1 and E2 are same elliptic curve, and you can have a non-trivial automorphism, such that a non-trivial automorphism, such that C1, the restriction of C1 and C2 are different. Then or equivalence. Okay. So the point is there's a difference between y0 and y1. If you think about the difference. So y0 is parameterizing E together with a cyclic subgroup of order n, but it did not pick out which generator it is. And for y1 it explicitly picked out a order n element. So you can think of it as, okay, so I have y0 of n, then I have y of 1 and right, this way and the y1 of n. So the point is here I have E together with a point, and then I map it down to E subgroup generated by Q. And then here I forget about subgroup and just map. So you can see this finite cover structure. Okay, so another way to think about a C point on y0 or n is, instead of using E of C, another way is to think about y(n)C. A point corresponds to a pair of elliptic curves E prime. Okay, and together there is together with isogeny cyclic of degree n. In other words, is giving you EC is the same as giving you E and E mod C together with this isogeny. Okay, so the point is the group C is just the kernel of person. It's the same data. Okay, you can also think it as parameterizing pairs of the curves together with a order n cyclic isogeny between them. Okay, and from our upper half plane perspective, my upper half plane model of gamma 0 of n, right? Then from upper half plane perspective, what you have is you take a tau inside H, and then associated to the point C mod, the first elliptic curve is explicitly Z plus Z tau, right? Then the second elliptic curve is given by Z plus n Z times n tau, right? And then the cyclic isogeny is given by Z to n times Z. So this is how we use a point in upper half plane to give rise to a C point in Y naught of n. And you can check this. You can check that this set of lattices are exactly parameterized up to action of gamma 0. Okay. The next important thing is that the modular curve x1, well, we define it over the complex number C, but it has a model over Q. Right? The point is, I can consider P1 over Q. Then if I tensor to spec C, then this is x1, right? So it has a model over Q as an algebraic curve. And I can even think it very explicitly, write its function field as Q adjoint J. Right? And the same thing for X naught of n. So X naught of n has an order, has a model over Q. What does that mean? What I mean is there exists. So first of all, we know that there's a map X naught of n mapping down into X naught of 1, right? We already discussed these maps. And X naught of 1 over C, okay, if we think about over C, then corresponds to function field C adjoint J, right? And then from the function field map between curves corresponds to field expansion. So I get C of J, right, adjoin some element X, mod out some polynomial f of X. This is irreducible. The field extension. Right. And X naught of what we're talking about is there exists polynomial. This f that we are taking, actually it has coefficients in Q. Q of J, then X. Such that we can take a f whose coefficients are actually in Q, such that the function we can have a curve, such that curve get curve X defined over Q with function field Q adjoin J, then join X, mod out f of X, and then this X tensor to spec C is just our X naught of it. So this is what we mean by it has a Q model. Okay. And another important thing is this polynomial f is actually not mysterious. This f is the capital phi, capital N of X tau, which we know that is inside Q adjoint J tau X from lecture 3. But in lecture 3, we did not prove that this polynomial was irreducible as a polynomial in X. We did not prove that, but it is true. This polynomial turns out to be irreducible and is actually the element that generates the function field of X naught of n. Okay, great. So this is what we will talk about X naught of n. And next comes from the super important fact, namely the modularity theorem. Okay, so if I take a point on a modular curve, some elliptic curve, maybe with some extra structure, if you x naught of n or x1 of n, right? But there's another way to associate relate modular curves and elliptic curves. So this comes the super important modularity theorem. So this theorem is often referred to as Shimura Taniyama Wei conjecture, and or since it's already proved, is often referred to as the modularity theorem. So this is proved by work of Wiles, Taylor Wiles, Conrad, Diamond, Taylor. And the statement is the following: is let E be an elliptic curve over Q there exists a positive integer n, such that the modular curve x naught of n admits a surjective map to E over Q. So this tells you that given any elliptic curve defined over Q, you can find a modular curve x naught of n. You can find n such that x naught of n admits a surjective map to E. So E can be covered by a modular curve. So, and this modularity theorem is the key ingredient in the proof of Fermat's law theorem. So this is this gives you another way to relate modular curves and elliptic curves. Okay, so this is what I want to introduce about modular curves. Next, well, so using this modularity theorem. So let's go back to the beginning of the motivation, right? I told you that we want to start in the rank of the curve, which means I want to be able to somehow count rational points on elliptic curves. And now I told you that given a elliptic curve, I can over Q, I can find a modular curve that admits a finite cover, admits a map to E, right? So this means if I want to construct Q points on E, one thing I can do is to construct rational points on this modular curve onto E, right? If I have a point on the upstairs curve under this map, give me a point on my elliptic curve, right? But then, unlike points on the curve, which are just solutions to this Weierstrass equation, points on which means we can construct rational points on this modular curve by constructing elliptic curve together with extended structure to give rise to a point on the modular curve, right? And so that we can actually construct points on downstairs elliptic curve. And well, which points are very explicit points on my modular curve? The CMT curves, right? If you think about the modular curve, even x, right? If I want to construct some rational points, some very explicit points on x1, well, you were saying that of course, like it's a p1, so any number gives rise to J invariant and everything, right? But if actually if you take any J invariant, it's you do get points on x1, but the curve is actually less clear because you need to invert J to find the corresponding tau to find the lattice you're looking at. But for a CMT curve, you have much more control about these CM points. And when you are looking at these modular curves, which are not x01, which has higher J-ness, there are less rational points, and it's even more difficult to construct a point from a non-CMT curve, just any elliptic curve. But in this case, when a curve has complex multiplication, it can help to explicitly construct points. Okay, so let's talk about how to use CMT curves to construct rational points on modular curves. So rational points. Okay. Well, so we're mainly thinking about modular curves, x naught of n, or maybe you can also think about x1 of n. These are two modular curves you'll be thinking about. Well, so both of them parameterize elliptic curve E with some level n structure, right? So x naught of n is a subgroup C. So this is a subgroup of E n torsion, right? And then x1 of n is parameterizing E with P, where P is literally element in E of n, which is order capital N, right? So this tells us that if I want to construct such a pair, I should study the n torsion subgroup of E. Okay, so recall. So let n torsion subgroup. We call that N are the set of points P on E. Let's do Q bar for now. Q bar such that NP is O. And also as a group is isomorphic to Z mod NZ squared. Mod N squared. Okay. Because the multiplication by N map is defined over Q, so we know that the absolute Galois group, Q for now, the absolute Galois group acts on the set of n torsion subgroups. Right? This actually gives rise to a Galois representation. A Galois representation meaning that a homomorphism of Q bar over Q to the automorphism of En, which is nothing but Z mod NZ, is the group is Z mod NZ squared, so its automorphism is GL2 of Z mod NZ. So this gives you a group homomorphism from the absolute Galois group, GL2 Z mod capital NZ. So if a subgroup C, cyclic order N subgroup of En, such that Galois, the Galois is it, meaning that this action restricts action on C, then the pair EC gives rise to a point, to a Q point, gives rise to a point on X naught of N over Q. Right. Similarly, if there's P of order N, P of order N fixed by the Galois action, then the pair EP gives rise to a point on X1 of N over Q. Okay. So the point is now the problem is the problem of rational points on the modular curves are very concretely related to the existence of a unity curve defined over Q together with some n torsion subgroup or n torsion point that is also defined over Q. So the point, for example, this part here proved his theorem, showing that there does not exist any unity curve defined over Q who's with a rational torsion subgroup of order rational torsion point of order greater than greater or equal to 13, for example. It's by showing that x1 of n, when n is greater or equal to 13, it does not have any point on Q on this curve. So starting rational points on modular curves gives you structure, tells you structures about. Okay, so now, what does CM point give us? So, well, okay, so how CM points, CM picker. What's special is that we have endomorphism alpha. So let number field. Let E be a let alpha be an endomorphism E to E defined over Q. Sorry, defined over K. the Galois group, absolute Galois group of K, well, it also acts on the set of n torsion points of E, right? But then this action commutes. So the image of this homomorphism commutes it commutes with the image of alpha, the induced map of alpha outside on E of n, which forces its image to be abelian. So this automorphism group was a GL2, right? But in some sense, if your elliptic curve has Cm, then once you base chain to the neighborhood K where the complex multiplication is defined, Galois image becomes abelian inside GL2, which is essentially has to be diagonal, right? So so the idea is, and this is in contrast to a non-CMD curve, namely a theorem of Serre. This is called the open image theorem. So Serre showed that let K be a number field, and let E over K be an elliptic curve without Cm. Then, if I look at this, so if I call this homomorphism phi of n acting on the n torsion, I can let n grow as big as possible, right? I can take a prime L and consider phi L to infinity. This actually we already discussed in the very first lecture of class. I can take such an inverse limit, essentially consider how the absolute Galois group acts on the L infinity torsion, okay, is of finite order inside the automorphism of E L infinity. And this automorphism group is also literally just ZL, it's GL to ZL. And two, actually, phi L infinity is a surrogate for all but finitely many L. Any primes. So this tells you that in general, when a elliptic curve does not have complex multiplication, this Galois action, the image of this Galois action is really big. It's almost all. For most of the capital N, this will be surjective actually. But when your elliptic curve has its image is way smaller. What does that mean? That means that of CM elliptic curves are defined over relatively speaking, relative to a elliptic curve with non-CM. And this fact applications in current research. For example, people are very interested in the set of points on curves that are defined over field. And when this curve is a modular curve, the CM point gives you a lot of low degree points. That's the first thing. Second thing is this abundance of CM points helps you to study. There are many more applications that I don't have time to discuss today. Then I want to say was when we were talking about the beginning, I told you that So work of Rostagi and Kolyvagin used CMD curves to construct a rational point curve called Higner points, and it uses the modularity theorem. So the idea is the modularity theorem. So idea is I want to construct rational points on E, and I do that by constructing rational points on the modular curve x naught of n. And how do I construct rational points on x naught of n? I take CM points. So let me just very quickly use 5 minutes to talk about picking the points. Okay, so the idea is let me first define Higner points. So let O in an imaginary quadratic field be an order. This is an order. And then a Higner point on y naught of n is a pair of elliptic curves E together with a degree n cyclic isogeny such that the endomorphism ring of E and the endomorphism ring of E prime are both O. So it's two CM little curves, both CM by O, together with a cyclic degree n isogeny between them. So such a point is called a Higner point on Y. Such points exist. Such a point exists when when D equals B squared minus 4nc. Okay, let me explain. Where n is our capital N, D is discriminant of O. Has integer solutions. Has an integer solution BC satisfying that BC are co-prime to N. Okay. When this condition is satisfied, such Higner points exist on the Higner point given by O exists on this y naught of n for this capital N. Okay. Okay, great. So then what we can do is for fixed O, take all Higner points with respect to this O, which is P1 ... through P H of O. This is the class number of O. So these are the number of Higner points on this. Let's just say x naught of n. It doesn't matter whether x naught of n or y naught of n. Okay. And then we know that if you have an elliptic curve such that x naught of n dominates the elliptic curve, we can actually make data points. Okay. And on the elliptic curve, because we have addition law, we can add up these images. This will give you a point which often denoted as P of K. This is a point over K. Okay. And then under some conditions, well, we can furthermore construct the complex conjugate. Now this is a point in E of Q. Okay. Under some conditions on the L function, of E on gross target was able to show that point pk plus pk bar has an infinite order, not torsion. Thus, we know that they generate this is an infinite subgroup of EQ. So this means that the rank is at least 1. And so it related the L function of E to the rank of the elliptic curve E, given evidence to the BSD conjecture. Moreover, with the work of Kolyvagin, actually this confirmed the BSD conjecture for large family of elliptic curves. Okay, let me finish here and continue our discussion next week. Thanks for coming.